Greetings, everybody. We had a request to do some videos on the mechanisms found in test 2. We're going to do fall 21, test 2, which is very similar in format to your test. And I'm going to share my screen. And here it is. And we got a combination of Fischer Esterification in our first mechanism and Acetal formation. So two very important reactions. We'll do one in its entirety. We'll do Fischer first, and then we'll do the Acetal formation. So we will take advantage of some colors to save a little space and time. Red first, and we'll use our favorite light blue second. Yeah, blue second, here we go. So if you're going to do a Fischer esterification, you need a carboxylic acid and one alcohol, sorry. We have a carboxylic acid here, and we have an alcohol here, HOET, ethanol. So we're going to do a little R action until we need this portion. We're going to protonate our carbonyl to make it more attractive towards the poor nucleophile. How am I going to do that? I'm going to bring it around underneath here. And that gets a lone pair. And then the alcohol, poor nucleophile as it is now more attracted to the carbonyl. And it attacks. And we're going to generate an oxonium. I won't combine a third step. I could, I won't. We're getting R attached to a carbonyl. There's no longer a carbonyl, it's an OH. It had another OH already. And the new stuff in black, we have an O with an H and an ET. It's an oxonium. And we have to deprotonate the oxonium with the OTS minus that I just made. So I made TSO minus right here. And we're going to deprotonate. And what we get there is what would be considered the hydrate of the ester. Hydrate of the ester. That means it has H2O extra over what an ester has. It's got the O ethyl group that an ester would have. And we need to make it lose water. And to do so, you've got to protonate one of the OHs to make them into a better leaving group. I'll choose the bottom one. You made HOTS. You're going to be using OTS minus in the next step, so let's have it ready. First step is to protonate to make a better leaving group. And leaving group leaves off of the strong acid. Not too pleased with where that arrow started. Hit the H, start in the middle of the bond and dump a pair there. Second step, we can now dehydrate now that we have a better leaving group. Grab H, sigma makes pi, leaving group leaves, classic elimination. Better draw our R group now because we are about to start our acetal formation mechanism. Looks like 1, 2, 3, 4, 5. 1, 2, 3, 4 CH2s. 1, 2, 3, 4 CH2s. Then CO2ET. We just made the CO2ET. Let's do an R prime out here. R prime. And now we have to protonate this carbonyl to make it more attractive towards ethanol in the formation of the acetal. So you're going to protonate first. Oh, that's HOTS. protonate first. Then the poor nucleophile is going to attack the carbonyl. And this time I will combine. I'm going to take the OTS that I made in the red arrows and neutralize the oxonium on the spot. Just trying to save a little space here. We'll do that in purple. Doesn't like me on the bottom of the screen. I keep forgetting that. There we go. And not liking where my little blue arrowhead ended here. Let's take him outside this array of arrows. Oh boy. I'm gonna have to make my screen a little smaller on this end so I can grab the bottom. Sorry about this. Wow, it's not doing what I want. Okay. I got my blue arrow going over here now. And we have our R attached to a carbon that now has an OET on it. What else is on that carbon is our R prime. That was our prime to start with, sorry. And we have a green OH. Hey, that's a hemiacetal right there. This carbon right here, simultaneously an ether in the bottom direction and an alcohol up to the green. So hemi is halfway to acetal. We have to get rid of the green OH and have another OET come in on the scene. So how do we get rid of the OH? Well, let's make it a better leaving group. Step one, make it a better leaving group. HOTS, lone pair, protonate. Now, don't try to do a backside attack on a carbon that's a hemiacetal. They don't happen. You're going to generate a second oxonium like you generated this first one with the red arrow here. The red arrow makes an oxonium that gets attacked, but we have to generate the oxonium first. So to generate the oxonium with a pi bond, you kick off the leaving group with a lone pair on the O. That's what makes it leave. And we're going to generate something that's a little, running out of space here. Let's see, we got ethyl with an O and a double bond to a carbon that also has an R prime. There you have it. We have to have that attacked by ethanol and then take the proton off the oxonium that will be on the ethanol. Will be on the O that has the ethyl group is what I should have said. So you're going to attack. There's your second OET. And we'll neutralize. And if we neutralize, I think we can go straight to our product and save a little time. We made OTS minus, so let's just have it under the arrow here. Baby blue. Neutralize and make our acetal. And I'll just get rid of my blue arrow. I wonder if I can. And that leads us to the product, which is right here. Okay. Acetal and ester. Next, we're going to do what's called aminolysis. That's a chapter 18 reaction where an amine or ammonia, they both do similar things, will hydrolyze our ester. Oh, wait, we got more than aminolysis here. I wasn't looking at my whole thing. And there's a reason why this thing is 12 points. Not only are we losing the OET, we're also losing the carbonyl. Oh my. And we're getting a nitrogen attached here. My goodness. That's the Hoffman rearrangement. But when you study the Hoffman rearrangement, you realize you need a primary amide. Oh, step 1 generates a primary amide in the aminolysis reaction that I was talking about. Okay, I'm sorry, I was just thinking out loud. And yeah, we're going to do aminolysis followed by Hoffman rearrangement. So aminolysis, it doesn't need to be activated because an amine is a more reactive nucleophile than is an alcohol in our previous example. So we don't need to activate our carbonyl. We got excess NH3. Let's see, I already have the R from before. Well, no, we can redefine our R from before. I don't need any of this stuff. We call it RX, prescription for success. And our ammonia, I'm going to redraw ammonia just so I can save time with it a little later. We got NH and 2 more H's. First step, you're going to hit the carbonyl. Pi breaks before sigma and becomes a lone pair on the O. And then the lone pair on the O comes back in the second step, kicks off the leaving group. The leaving group would be, and we'll go with a black arrow here. The leaving group would be ETO minus. And I hope you know that ETO minus is definitely a strong enough base to deprotonate an ammonium ion, and a neutral nitrogen that makes a 4th bond, which is what this mechanism says, is going to generate an ammonium ion. And yes, this base will deprotonate the ammonium ion in a step 3. And there's your aminolysis. We'll show the product right here. We got RX attached to a carbonyl that has an N, and we'll put it in blue. 2 H's. Step 1 is over. We did it all in 3 steps. Attack, neutralize the oxonium. Sorry, what was it? Attack, pi breaks, then eliminate to get your pi back, and then neutralize your oxonium to make this species here a primary amide. Hey, primary amides can undergo decarbonylation. What do I mean by that? If you look at the result, the carbonyl gets removed and RX is attached to NH2. This is RX all the way up to this carbon here. And the end result is decarbonylation, but there's a lot of steps. This is our biggest mechanism on this test. And what we're going to do first is use our base, hydroxide, deprotonate your amide, pKa 17. We did that in class the other day. That arrow does not really start on the lone pair. No, it does. Except it's not really an arrow. Okay, I'm going to stop that. RX attached to carbonyl that has an NH minus. A strong nucleophile that will attack Br2. In this fashion, attack, leaving group leaves. And you get this N-bromo primary amide. And that's even more acidic than the original. So the hydroxide number 2 is doing this faster than the first hydroxide did that for its reaction. And here's where the fun starts. And a lone pair minus. In fact, I think in class we saved a little time by resonating all the way up to the O minus. And I think I want to do that again. Let's see if I can do that. I got 2 arrows there. It's going to be harder than I thought. Maybe not. I'm resonating up to get an O minus. Really didn't change much here.
We did resonate in class.
Yeah. Double bond, O minus, which could resonate back, but that wouldn't get us anywhere. Or instead of resonating back, when the pi reforms, the carbon group moves. And yes, this is called a Hoffman rearrangement because of this one step here. This is the Hoffman rearrangement. Rx is attached to a carbonyl. No, it's not. Rx is bonded to nitrogen. Look, take its electrons and move to the nitrogen. Let's try to show it with minimal atom movement here. The N is bonded there. And the N has a double bond to C, which has a double bond to O. I know it looks goofy, but try to keep atoms almost in the same position. It's an isocyanate. And it's finally got the nitrogen attached to Rx like our product needs to have. But we also have to get 2 new H's on there and get rid of our carbonyl. And that involves a lot of manipulations with hydroxide and water combined. Multiple times. I'm going to do HO minus. I'm going to have a little H2O right up here too. Step 1, HO minus is attracted to that very positive carbonyl. It has 4 bonds to more electronegative atoms. And lone pair on oxygen comes back. Baby blue. Comes back, and the nitrogen picks up a proton from water. This is acid-base pair that's a catalyst, right? Hydroxide's used here, and hydroxide is made here. And what we're getting here is this species here. We'll tidy it up a little bit. Rx bonded to N that now has an H. And a single bond to carbon, which does have a double bond to O. But this O now has a new OH on it. And remember in class, we called that a carbamic acid. Carbamic acids are not stable species. So step 1 to get rid of the carbonyl here, acid base on an acid with a strong base is no surprise at all, I hope. Carbamic acid, when there's strong base present, must react first. And it's at this time I remember this final product, CO3 2- implies that the third O has to come from somewhere, and your best guess for a third O coming from anywhere is always hydroxide in this particular mechanism. Large excess. So your next step, hydroxide comes in and attacks the carbonyl. Pi breaks. We've got Rx attached to nitrogen, attached to H, attached to carbon that's not a carbonyl anymore. No minus. It's got another O minus. It's got a new OH. And I believe I finished this thing off in class by doing an elimination that looked a lot like a tautomerization, but then again, all eliminations look like tautomerizations. And somebody would eventually point out to me this hydroxide is going to lose a half point on the test because it's not an ide. There's a charge. Yeah, my goodness. Okay, I'm going to use my last hydroxide that I have to use, and I'm going to use a water to provide the second proton for the nitrogen. Much the same as water provided the first proton for the nitrogen here. Hydroxide is going to grab that H. Sigma becomes pi. Leaving group can only leave if we protonate on the way out. And there's your hydroxide back, meow, meow. And we get RxNH2. These are the products at the top of the screen. Just want to see them all here. Got 2 new H's. We also generated carbonate. Oh, double bond to C that has O minus to the left and O minus to the right. And that's our final results right there. Put them in yellow, I guess. And big picture for the whole deal. There's a lot of deal there. Yeah, a lot going on there.
Yeah, that one's hard, the last one.
With practice, you know it's coming though, I'm telling you. So
Yeah.
with practice, I think if you can handle the from 241 hydroboration oxidation, this one's got more
Those were
repetition.
easy.
This one has more repetition than that one. So even though it's a
Okay.
little longer, I think with practice you can get there.
Yeah, I think it'll become easy with like, the
Students
more do it.
usually do get there because they know the teachers basically said it's on the test, and they do what they have to do to get all the steps down.
12 points when you say that.
Yeah, 12 points. You just keep focusing on that and say I can't skip that.
Yeah.
And off video, we did discuss doing 2 and 1 here, but I think this was long enough for one video. We're going to come back for our next video and do the same exam, but we're going to do part B. So see you then.